So being the last speaker, first I would like to thank Ben for inviting all of us. And this is a wonderful workshop, and we had a great time. So I'm the last speaker. Today I will talk about, as the title suggests, the optimal design of dynamic mechanisms without transfers. More specifically, this is joint work with Johannes from Yale University. So more specifically, we look at a very stylized model in which the agent is able to evaluate the changing state of the world. And a principal who has commitment power also will have the decision rights over the allocations in every period. And there is no transfer to facilitate truth telling between the agent and the principal. Moreover, there is no hard evidence, possibly statistical evidence about the agent's private information either. So in this case, as you can see, the only instrument that the principal has to discipline the agent is future allocation decisions. So we are interested in solving for the optimal mechanism for the principal. Okay. So let's start with a toy example between a patient and a nurse. So this patient is our agent and this nurse is our principal. So in every period, the patient's condition might be severe or mild. So if his condition is severe, he values the nurse's attention very much. And if his condition is mild, he also wants the nurse's attention, but not as highly as in the severe condition. On the other hand, the nurse, he incorporates the utility of the agent, but he also incorporates the cost of supplying, of paying attention to the nurse. So he only wants to pay attention to this nurse if and only if the condition is severe. Okay, so there is a conflict of interest between the two players. So this may sound like a very, very toy example, but alarm fatigue is a real problem in the health care industry. So now let's look at more general other applications of this toy model. So managers want to go ahead for their projects, but the headquarters, they prefer to initiate these projects if and only if the profitability is very high. But the managers want to initiate these projects even if the profitability of this project is not as high as the headquarters demand. And also the state departments want to expand, and the cities or states want more resources. So these are the applications we have in mind when we started this project. Now, we have three main questions. The first one, is there a simple optimal policy we can solve for in this kind of environment? Secondly, how does the agent's utility and the principal's payoff evolve over time? So our principal is a social planner, so his payoff is also the efficiency of this relationship. And how does this optimal policy depend on the lack of transfers? In other words, in the end, we want to compare the dynamics and the optimal policy with transfers and the dynamics and the optimal policy without transfers to see the role of transfers in this kind of dynamic mechanism design problems. Okay, these are the three questions we will answer, hopefully by the end of this talk. Now, our paper is related to a large literature, and for the sake of time, I will focus on three papers. The first paper is this paper by Jackson and Sonashan. So they solve for a symptotically optimal mechanism in this kind of environment. Let's go back to the patient and nurse example. If this patient lives in this hospital for 100 days, and in every period his condition is equally likely to be severe or mild, a very natural way to discipline this agent is to give him 50 tokens. So by each token, he can buy 1 day of care. And if he lives in this hospital for 1,000 days, 1,000,000 days, the efficiency loss of this token mechanism will eventually go to 0. And our paper is different than that token. We will show that the optimal mechanism in our environment is different than a token mechanism. So we are interested in exactly optimal mechanism, and we have a fixed discount factor. So that means every period matters in our environment. And that's the main difference driving the difference in results. Now, the second paper I will discuss is this AR paper by Battaglini. So this paper looks at the exact counterpart of our model with transfers. So by the end of the talk, I will compare our optimal mechanism with the optimal mechanism in that paper to see the role of transfers in these design problems. Okay. And the last paper is this paper by Thomas and Warren. So they look at an insurance problem between a risk-neutral principal and a risk-averse agent. And the analysis of our IID case model, IID model borrows a lot of ideas from their papers. But there is a crucial difference in terms of long-run dynamics. In the long run, they show that the agent will get his worst possible outcome in this relationship. It's called immiseration. In our model, in the long run, the agent will either get the worst possible outcome for him or the best possible outcome for him. So we call this polarization. And I will come back to that after we talk about the IID case. Okay. So if there is no questions, I'll move on to the formal model. Okay. So we look at the discrete time model, and we use n to denote the time period from 0 until infinite. And agent's type, or the agent's value in each period, is denoted Vn. It can be either low or high. Okay. The cost to supply this unit is given by C, and this is a positive number. And we look at the only non-trivial case in which high value is higher than cost and is higher than the low value. And the low value is higher than 0. So that means the agent always wants this unit, but the principal wants to supply it if and only if the value is high. Now, the value follows a Markov chain with one period of memory. So conditional on my value in period n being high value, my value in period n plus 1 is high with probability 1 minus rho h. So rho h is the probability of mutation conditional on being a high type today. Similarly, rho L is the probability of type rotation conditional on being a low type today. And specifically, we look at a case in which 1 minus rho h is higher than rho L. So h value, high value, is more likely to be followed by a high value than a low value is. So in other words, we look at perfect persistence. So there are two special cases. When 1 minus rho h is equal to rho L, that is IID case. And when rho L and rho h are both equal to 0, that is the perfectly persistent case. So these are two special cases of our model. Now, the invariant probability of a H type and the unconditional expected value of the unit are given by Q. So this is the invariant probability of a H type in this relationship, and mu is the average value of the agent for the unit. Okay, this is our model, very simple and very stylized. Now, they share a discount factor delta. So this discount factor is fixed. So because we see the principal as a social planner or welfare maximizer, so we see no reason to talk about different discount factors for the two players. And then Xn is the principal's supply decision in every period n, which can be either 0 or 1. So given this sequence of supply decision, the agent's utility is the discounted sum of his utilities from consuming the units whenever they are supplied. And the principal's payoff or welfare is the discounted sum of the agent's utility minus the cost of supplying this unit. Now, in each period, the agent makes a report M, and the principal makes a decision or supply decision. In this stylized environment, the principal has commitment, so it is without loss to look at direct and truthful mechanisms, in which case the message space is a type space, is either low or high, and the agent always tells the truth. Okay. So in this case, a policy or a mechanism is a map, xn. Each map maps the sequence of past reports to the supply decision in this period. And this policy defines a decision problem for our agent. And we look at the case in which the agent always tells truth given a policy. Okay. For today's talk, I will start with the very simple case, the ID value, and then I move on to the Markov case. And if we have time, eventually I'll talk about the optimal mechanism with continuous types. But I suppose we don't have that much time. We'll see. Okay, so the ID case is very simple. So if the agent's value is ID without the loss of generality, the agent's ex-ante utility is a valid state variable. We can use this valid state variable to summarize the continuation play. And now a policy is represented as a map from this U is the agent's promised utility to the current period's decision as a function of the agent's report. So in other words, a policy maps from U to 4 numbers. PH is the probability of supplying this good if the agent reports high. PL is the probability of supplying the good if the agent's valuation is low. And UH is the agent's promised utility from tomorrow on. And UL is the agent's promised utility from tomorrow on, conditional reporting low today. Notice that all the utilities from 0 to mu are feasible promised utilities. So we can always find an incentive compatible policy such that we can deliver any number between 0 to mu to this agent. Now we can write down the principal's problem, which is Markov with respect to the state variable mu. And the principal wants to maximize his payoff subject to the constraint that the agent's promised utility is U ex ante. And for any type, L or high, it has no incentive to mimic the other type. Okay. Now, the principal's payoff is given by the sum of this period's flow payoff and his payoff from the continuation play. Okay. Questions? Good. Now, I'd like to start with a complete information case. So this is the same program without incentive compatibility constraint. So we still keep the promise keeping constraint. Now, if that is the case, also if the initial promised utility is freely chosen, we know that the best thing to do for the principal is to supply the good if and only if the valuation is high. So that is a stationary first best policy. And the promised utility for the agent is constant and is given is fixed at QH. But if we cannot choose the promised utility freely, we know that we have to distort from that very first best policy. And I use a gray color here because it's better to look at the picture than the formulas. So this picture shows the first best, the complete information case without incentive compatibility constraint. The x-axis is the agent's promised utility, and the y-axis is the principal's payoff. And QH is the very first best for the principal. Below that, the best policy is to provide only if the valuation is high. Above that, the best policy is to provide if the valuation is high, but I also need to provide the unit when the valuation is low with some probability. So this is the first best, and this we already, by observing this picture, we can already solve the second best case. Okay, so let me show you how to do that. Okay, this is mu, this is QH. So we make 2 observations about the second best. The first observation is that we always want to implement efficient allocation as long as possible. So the qualification that as long as possible happens when the promised utility is very close to 0 to mu. In that case, we cannot implement the efficient allocation because, for example, if the promised utility is 0, I can never provide it. And if the promised utility is mu, I need to always provide it. And very close to these 2 points, we have to distort away from the efficient allocation due to promise keeping. But if we forget about those peripheral regions, we can always implement the efficient allocation. And it's best to implement efficient allocation. This comes from the observation that the second best is below the first best. And the second best is the same as the first best at these 2 endpoints. And also, we know that second best is a concave function. So if we draw a picture here, we know that the second best slope of this welfare function is below h minus c over h. And here, it has to be above L minus C over L. Okay, this is the slope of the first best in this region. And that's the slope of the first best in that region. So the slope of this second best function has to be between these 2 numbers. This is a negative number and this is a positive number. So that means if the high type is not getting the good with probability 1, suppose this is high type's promised utility and the pH is smaller than 1, I can always increase pH by a little bit and decrease UH by a little bit to satisfy promise keeping. But in this case, IC constraints are not violated, and the principal is better off because of these slope constraints. Okay, because by increase pH, I get a payoff increase at the rate of H minus C over H. But by decreasing UH, my payoff is decreased at a rate that is bounded from above by H minus CH. Okay, so that's the intuition why we always want to implement the efficient policy. Intuitively, there are no better times to cash in the agent's promised utility when the agent's value is high. Because when the agent value is high, their interests are aligned. The principal would like to provide the good to decrease the promised utility, to redeem the promised utility. And there are no worse times to cash in the promised utility when the agent's value is low, because future valuations will be higher than low on average. So the principal prefers to wait until later times. So in this case, we have efficient allocation at the very beginning. So that's very different than the mechanism with transfers, because with transfers, they would like to, backload the efficiency. So asymptotically, the future allocations are always efficient. But here, we front-load efficient allocations. Okay. Now, the second observation is that one IC constraint always binds. This is a low-type IC constraint. Given that the payoff, the welfare, the W function for the principal is concave, it's not a good idea to spread the promised utilities. So I would like to spread it as much as, I would like to spread it as little as possible, but I still have to satisfy the low type's incentive compatibility constraint. The low type is not provided the unit. He would like to mimic the high type given the efficient allocation. So in the end, IC constraint of the low type always binds. So this solves our second best problem already, because we only have 2 unknowns, UH and UL. We have 2 equations, ICL and the PK, promise keeping, and the low type's incentive compatibility constraint. And also you can see this is different from the standard adverse selection model with transfers. With transfers, high type would like to mimic low type to avoid paying a high price. Without transfers, low type would like to mimic high type to get more allocations. So this almost concludes our second best analysis of the IID case. Let's look at more details. Okay, so we have 2 equations, IC low and promise keeping, and we have 2 unknowns, UH and UL. So first of all, both types are willing to say that they are high type. So the promised utility ex ante is equal to the flow payoff if both types say they are high, and the continuation payoff of high type. Okay. Secondly, this tells us that if you tell me you are high type and I provide the good, your continuation utility is lower than your ex-ante promised utility. This is because mu is the highest possible ex-ante utility we can have, and u is a weighted average of both. Now, secondly, the high type will has 1 minus delta multiplied by h minus l excess utility from mimicking a low type. So he is not willing to mimic low type. He has to be given this excess surplus. Now, we can write the promised utility as the sum of the excess utility and the agent's payoff if both of them say that they are low. Okay, so delta UL is the low type's payoff, and this is the excess utility for the high type. So this allows us to solve for the promised utility from tomorrow on. And here you can see UL will be smaller than U only if U is smaller than Q multiplied by H minus L. So if the promised utility U is sufficiently low, the future utilities are trapped below that level. And that is a fixed point region, and we achieve the first best. Beyond this lower bar, we know that we only have second best, which is strictly below the first best. Now, we have two regions. When the promised utilities are sufficiently low, the agent is willing to wait for the high type valuations to ask for the unit, and there is no efficiency loss. And when the promised utility is high, we will have a transient region as well, and eventually the utilities will spread until it gets absorbed either in the first best region between 0 and the U lower bar, or it gets absorbed at the highest possible promised utility the agent can have. The drift of the agent's promise utility follows from our promise keeping. So from promise keeping and our second best optimal policy, the flow payoff the agent will get is equal to QH. So if the promised utility is above QH, the expected promised utility from tomorrow on has to be above today's promised utility. On the other hand, if the promised utility is below QH, the expected promised utility from tomorrow on has to be below my today's promised utility. So they will drift up above QH and drift down below QH. Okay. So that's our analysis for our IID case. And are there any questions so far? I'm moving a little bit too fast. Okay. So now let's summarize our. Thank you.
So could you briefly comment? This seems somewhat related to this Hauser-Hoppenheim. Can you comment on how this?
Oh yes, yes. So there are many differences between our two papers. So first they look at. So let me summarize it. They look at a favor trading game between two players. So they look at repeated games. We have commitment, and they have. At a random time, one player will privately observe a chance to give favors to the other guy. So in this case, it will become clear after we talk about the continuous limit of our model. So the continuous of our limit of our model is a model in which the agent's value changes at random times, and it can be either high or low. Okay, so this is our technology. In that paper, they have a technology in which we have random shock, and at these shocks, it's good to provide the good. So we have a flow payoff technology. They have a lump sum payoff technology, and this has persistence. This does not. And beyond that, I also think that the analysis is very different, but there is a similarity. They also show that the IC constraints have to be binding all the time. So that's the best way to trade in favors instead of using token mechanisms or chip mechanisms. So that's a similarity. But beyond this, questions? Okay. Now, let's summarize the second best result formulae. So the optimal policy is to supply the good if and only if the valuation is high. And I use gray area to summarize the two endpoints. And the payoff function W, so the second best payoff function is linear and is equal to the first best when the promised utility is sufficiently low. And is strictly concave and below the first best for higher promised utility. And we can also prove that this payoff function is once continuous differentiable over all the regions with a limit that is equal to the first best at the two endpoints. So at these two endpoints, it's basically the boundary conditions that are binding. So that's why we can get the first best slope there. And optimal choice of the promised utility for the agent solves this first order condition. Okay. So this is a picture that summarizes our result. And the principle will start from this promised utility such that the slope is equal to 0. And whenever the agent asks for the good, the utility drifts down. And whenever the agent does not ask for good, the utility might drift up or drift down, depending on whether we are in this region or in this region. Okay. Now, from Thomas and Warren's paper, we have this Martingale property of our payoff function. So the derivative of the payoff function is a Martingale. That means we can calculate the eventual absorption probability of two endpoints. And we start from derivative 0, and eventually we either get absorbed at 0 or we get absorbed at mu. And these are the slopes at 0 and mu. So we can calculate the probability of getting to the worst possible outcome for the agent, and 1 minus alpha, the best possible outcome for the agent. And this absorption probability does not depend on the discount factor, only depends on H, L, and C. Okay, the first step. Questions? Now, to implement it, you can see that this is not a token mechanism because the agent's report not only affects whether he gets the unit today or not, it also affects how many units on average he will get. And we will implement this using a budget mechanism. So this phi is, we define this f, which is equal to 1 minus delta multiplied by our lower bound of promised utility. And the g is equal to 1 minus delta multiplied by the expected payoff if the agent gets this unit today, minus f. So the way to implement it is very simple. The principal will give the agent a budget of U star. Now, at the very beginning of the period, he will charge this agent a fixed fee of f. And if the agent asks for the unit, he will charge this agent another fee, another price of g. And at the end of the period, he will give the agent an interest payment based on the agent's current budget. And the interest rate is equal to the discount rate of the agent. So this will exactly implement our optimal policy in this environment. Okay. So here we would like to make a few observations between our mechanism and the token mechanism, because frequently people will ask about this question, why not using a token mechanism in this simple environment? It's very intuitive and a very natural way to discipline the agent. So we want to see the performance of token mechanism versus the performance of our mechanism. But if we want to make this comparison, we have to distinguish two different models. One is a static model in which the agent is a profit. So the agent knows the realization of his valuations from at the very beginning. He knows the realization of his valuations in every period in the future. We call him a profit in this case. And in our environment, the agent is a forecaster. So he only knows the realization of his valuations up to time t when he makes the report. And that means his report is predictable subject to his valuation realization up to time t. So under these two models, the comparison will be very different. Okay. Now, we have two questions. The first question is that, are the token mechanisms optimal in these two environments? The second question, if this answer is no, what's the performance of the optimal mechanism in these two environments? Okay. So now let's look at the first question. Are the token mechanisms optimal in these two environments? Now, if we have a profit agent who knows everything at the very beginning, and we have a forecasting agent who knows his valuation up to time t, and we look at the token mechanism, it doesn't matter whether the agent is a profit or forecaster. The agent will behave in exactly the same way, whether he knows his valuations in advance or not. This is due to our binary valuation assumption. In these two environments, the agent will always claim the high value units if he still has tokens in his backyard. And he will always decline the low value units if the remaining tokens cannot cover the remaining periods. So in that case, Jackson and Sonnenschein, they have proved that the token mechanism is asymptotically optimal if we have a profit agent. That means it's also asymptotically optimal if we have a forecasting agent. That's exactly the answer to your question. So as delta goes to 1 or as t goes to infinite, and the token mechanisms are asymptotically optimal. Now, and also we know that difference in information between two models plays no role in this environment. And the loss, the efficiency loss is of the order which is to the reverse of the square root of t. Okay. This comes from a law of large numbers. Okay. Now, the second question is, are the token mechanisms optimal in these two environments? We know that token mechanism is not optimal here, right? We have shown that the optimal mechanism is not a token one. It's not a discounted token one either. And in the paper, we have proved that with a static model, with a profit agent, the token mechanism is not optimal either. So this is because in this environment, the agent has two types of information. He knows whether this unit is of a high value or no value, okay? And he also knows how many units are of high value. So the token mechanism is not taking advantage of the second type of information. And that's why it's not going to be optimal in this case. We can show an improvement of token mechanism. So the answer is no for both types of environments. Now this leads us to the second question. Is the principal better off facing a forecaster or facing a profit? And fancy a guess, which one do you? Okay, so at the beginning, the intuition is that the principal should be worse off here. And the intuition, most of the people will say, okay, the agent has more information in this environment. The principal has to be worse off. But that intuition is not correct. It's not entirely correct. This is because this is not a zero-sum game. And the agent has more information here that might benefit our principal, because the principal might induce a better fit between how many units are high valued and how many units should be allocated. We can come up with examples of 2 periods, 3 periods, or 4 periods in which the principal is better off in this environment. But luckily, asymptotically, we can make the comparison. So as we take t to infinite or we take delta to 1, the principal is better off facing a forecaster than facing a profit. So this is because even if we can take advantage of that additional information, the benefit from that additional information eventually vanishes. So that means the rate of the optimal policy, we can prove that the rate of the optimal policy is still the same as the token one. So the token one can be improved upon, but only marginally. But in our environment, with a forecaster, the rate of efficiency loss is linear to 1 minus delta. So we only lose the information rent in the first period in our environment as delta goes to 1. So that means if you want to use a token mechanism, I would say it would not lead to a very large fraction of efficiency loss if you use a token mechanism when facing a profit. But it will lead to a sufficiently large efficiency loss if your agent is a forecaster. It's better to use our budget mechanism in this environment. Let's move to the hardcore model, the Markov case. Okay. So when we move to Markov values, everything we have done in the IID case has to be put in the trash bin because we don't learn much from our practice with IID values. And now with Markov values, let's first look at our model we have introduced at the beginning. So if my value today is high, my value tomorrow is high with probability 1 minus rho h. And if my value today is low, my value tomorrow is low with probability 1 minus rho l. Except now we have a strict inequality sign. It's not IID. We have perfect persistence. All else is the same. So we only change this information technology of the agent. Now, still, the revelation principle applies, so we can focus on direct and truthful mechanism. But the first difficulty we have is that promised utility is no longer a valid state variable. If we fix an incentive-compatible policy from tomorrow on, a high-valued agent today values this policy different than a low-valued agent today. So we cannot use this single promise utility to represent the agents, to represent the value of this continuation policy to the agent. Instead, we have to use a pair of promised utilities. We call it a pair of promised entering utilities, UH and UL. So if you tell me your type is today, your promised utility is UH. If you tell me your value is low today, your promised utility is UL. Plus, we have to track the principal's belief over the agent's type. That's given by this Greek letter psi. And this is the file psi. And this is the principal's belief that the agent is high type today. So with these three state variables, we can go back to our Markov problem. Now, let's look at the principal's problem. Given this state variable, psi, UH, and UL, the principal will decide the probability of supplying this good today conditional on the agent's report, H or L. And also, he will decide a pair of promised utility for the agent from tomorrow on, conditional on the agent's report, H or L. So now we started from UH, UL. This is the promised utility pair for the agent. And if the agent report that his type is H, he will get PH of getting the good, or UH, H. This is his promised utility if he reports high tomorrow, from tomorrow on. And ULH. Okay. And the low type will get PL. And here he will get UHL. This is his promised utility from tomorrow if he reports H tomorrow. And ULL. Okay. Now we can write down the agent's payoff if he lies today. If he is a high type and he claimed this this package for the low type, he will get 1 minus delta H PL plus delta. And he knows that he is a high type tomorrow with probability 1 minus rho H. But he will get this UHL tomorrow. And plus rho H ULL tomorrow. So this is the utility the agent will get from lying today. And we have to make sure that UH is greater than this. And applying the same equation to this bundle, that is promise keeping. So we have a promise keeping equation here, IC constraint here, promise keeping equation here, IC constraint here. And the one-shot deviation principle will apply here. So we are fine. Now, this is a program. Now the principal wants to maximize his sum of payoff from today and from tomorrow on, and given the state variable UH, UL, and psi, subject to the promise keeping constraint for the high type and IC constraint for the high type. The same two constraints apply for the low-type agent. So we have solved for our first problem. We can go back to this Markov stationary problem for the principal. The second problem is that we don't know the feasible set of UH and UL. We don't know what is the feasible set of the possible promised utility pairs the principal can deliver. In the ID case, it's very trivial. We know that anything between 0 and mu are achievable by some IC feasible policy. And if we move to the Markov case, the first observation is that not all promised utilities in that square will apply. For example, we cannot promise a high type 0 and a low type mu. That is surely not incentive compatible in this environment. Now we need to solve what we call the incentive feasible set, the set of all possible promised utilities that the principal can deliver, forgetting about optimality for the moment. Okay. Now, luckily, so we did a lot of computation and we did a lot of simulations and we come up with conjectures, and luckily for the presentation, the result is very intuitive. And this comes from two groups of policies. The first group is called front-loading policy. So under this policy, the principal will produce for the first n periods and never producing again from n plus 1 period on. The second group is called backloading policies. The principal will ignore the reports and producing starting from a fixed period on, but not producing before. So intuitively, you can see this will be the boundary of our feasible set. That's because if we fix the payoff for the low type, fix the payoff for the high type, the low type gets the highest possible payoff if we are using a backloading policy. He has time to recover. His type is, so the low type, if we use this x-axis as time and the y-axis as valuation, the low type is here, and this is the average mu. High type is there. And the expected valuation is going up for the low type, and it's going down for the high type. So this picture explains that why we want to use backload and front-load policies. If we fix the payoff for the high type, the low type gets the highest possible payoff under a backloading policy, and he gets the lowest possible payoff under a front-loading policies. So that's our feasible set. And of course, that's not a proof, but we prove formally in the paper that we only need to look at all the payoffs in that set. Okay. Now, this is our feasible set in this game. The x-axis is the promised utility to an agent whose type is high today, and the y-axis is the promised utility to the agent whose type is low today. And this lower boundary is front-loading policies, and upper boundary is backloading. So if we fix UH, the low type is happiest when he is using a backloading policies. And here, this V star is the promised utility to the agent if we use the very first best policy in this game. You can see that this very first best policy is not even in the feasible set. We can never achieve this point, even if we forget about optimality. Okay. Now, that's our second problem. The last problem is solved for the optimal policy. And we get a lucky shock again, because the optimal policy turns out to be very simple. When we come up with this problem, we have to solve for the optimal policy for every possible state variables. So that means we have to solve for the optimal policy for every promised pair in this feasible set, and for 3 possible beliefs of the principal, which depending on whether this is the first period or whether the agent's previous report is high or low, the principal's belief will be rho L or 1 minus rho H or Q, which is the initial period's belief. So we have to solve that problem, and we did that, and then we find out the optimal thing for the principal. It turns out if we only use the optimal policy for the principal, what will happen is that the optimal policy is simple and is independent of beliefs. And I will focus on the reachable subset if we implement this optimal policy. Eventually, the principal will only, the agent's promised utility will only lie on the front-loading policies. And this does not imply that front-loading policies occurs in this environment. And still, the principal always implement the efficient policy as long as possible. So he produces if the report is high, and he does not produce if the report is low. And also, he wants to shrink the different distance between the promised utility pairs after high and low reports as close as possible. So in this case, that means we have the efficient allocation in which the high type always gets the unit, and we have a binding low type constraint, IC constraint. So that means we will only land on front-loading policy frontier, because for any policy such that IC low is binding and the pH is equal to 1, the agent's utility is equivalent to a front-loading policy. Because low type is always indifferent between reporting low or high, and high type always gets a unit. So if we calculate the agent's promised utility pair from implementing that policy, it has to be a front-loading policy payoff utility pair. So that's why we can focus from now on the front-loading policy curve. So
is that obvious that in this environment, if message is high and that's like a true setting you want to give a good? Okay.
So it's not obvious to us at the beginning. So we tried many different variations. We think that if there are correlations across periods, the principal would like to take advantage of this correlation. And, but eventually, the proof shows that the principal still wants to front load and back load as long as possible. I think
but my concern is that suppose that the last period's report was low, so most likely you are low, but you say high, then the probability that you told the lie is kind of higher. So like not giving a good after that environment probably.
I agree with you. This can be shown from this. I think this can be shown from this IC constraint, right? So if we think about the promised pair, the indifference curve of a high type is going to be looking like this, and the indifference curve of a low type is going to be flatter or steeper. So probably we would like to take advantage of this difference in their the slopes of their indifference curve over UH and UL. So that's the intuition we had at the beginning as well. But eventually, I think the intuition from the IID case dominates this intuition of using all the different continuation payoff. I think, so we can show that the principal always want to push the promised utilities as lower as possible. And he, on this front line, beyond that, I don't, so beyond the IID, to be frank, beyond the IID case, I don't have very, very good intuitions for that, But still, if you think about this case, if you are high today, tomorrow your valuation is going to be lower. And either I cash it today, and both are happy. I give you a promised utility tomorrow. And you're right. In this case, the probability will drift to the two endpoints quickly. But still, I think the intuition from the IID case, I want to cash in as soon as possible, applies here. That's dynamics. And let's look at the picture here. Now, if we have these front-loading policies, and we can focus on these front-loading policies from now on, what we can see is that if the promised utility is sufficiently high, after high type, the future promised utility goes down. And after low report, the future promised utility goes up. And if the promised utility is sufficiently low, after high report, the future promised utility goes down. And after low report, the future promised utility goes down as well. And So the dynamics are very similar to the ID case because it's almost a one-dimensional framework. And what happens is that if you report high today, tomorrow your promised utility is going to be lower than your today's promised utility. And if your promised utility is sufficiently low, your promised utility tomorrow after low report is also lower than your today's promised utility. And the drift is the same intuition as in the ID case. If your promised utility is above the average utility that you will get under efficient policy, and your promised utility will drift up, otherwise it will drift down. Okay. And eventually the utility will get absorbed at either 0 or mu, and we don't know the absorption probability in that case. It's no longer a Martingale. Okay. So once we have this Markov case, we can implement it using a very simple policy again. And this goes back to the interpretation of our incentive feasible set. We always land on these front-loading policies. That means we can represent each point on this front-loading policy line as the number of periods the agent can ask for the units with no questions asked. Okay. So the optimal policy is to give the agent an account of the number of periods he can consume these units with no questions asked. If he does not ask this agent, we update this account based on the promise keeping constraint. And if he asks for it, and the IC constraint. If he asks for it, we'll subtract the value of this unit to a low type, and we update it based on the promise keeping and IC constraint equation again as well. So this is the universal way to implement the optimal policy in our environment. This also applies to the ID case. You can also interpret the ID as the number of periods under which the agent can ask for the units with no questions asked. Okay. And now it's a little bit surprising that we got like consecutive lucky shocks and we are able to solve it. And it's not surprising that we cannot get any comparative statics from this framework due to the discrete feature of our feasible set. Okay, this is, we try to find the effect of persistence on the principal's welfare, but we try different methods of proofs, but it doesn't work. So eventually we take a detour and we look at the continuous time limit of our Markov case. So we let the probability of mutation be proportional to the time length of each small interval. And we also, in this case, we take the timelines to be 0. And we can, after we do that, the model looks slightly different, but the spirit still remains. In this model, what happens is that, as I have mentioned before, we have a model in which the agent will get random shocks, and his value is high, and at a random shock is low, and at another random shock is high again. And he will talk or communicate continuously with the principal, telling him whether he has got a shock or not. And that will buy us two things. First, our incentive feasible set becomes smooth. And secondly, the principal's belief is degenerate. At each moment of time, I know that in a small second later, the principal's value is the same as the previous value he has. So in this case, we get this incentive feasible set, beautifully incentive feasible set, and this is the first best region. When the promised utility pair is sufficiently low, the principal can get first best. And also, we can solve for the payoff function. So the IC constraint and the PK promise keeping constraint will eventually become a coupled ODE, and we are able to solve this ODE and solve for the explicit formulas for our payoff functions, which is given by this slide. Okay. And the takeaway from this is that persistence hurts. Okay, now we are able to draw the payoff function for the principal. The x-axis is time tau. This is the time that the principal or the agent can claim the units with no questions asked. Okay, from 0 until infinite. And this first line at the very top is the principal's payoff from the first best, subject to promise keeping. And the second line is the second best given a fixed persistent level. And then we increase the persistent level, the principal's payoff will decrease point-wise. So that means similar to the case with transfers, in this case, the persistence of agents' information also hurts the principal. And so this, if you want to understand it, if we have perfect persistence, what can be done is the principal's optimal payoff given mu and c, right? If mu is higher than c, the principal always supply the good. If mu is lower than c, the principal never supply the good. So that's the worst possible way for the principal in this environment. Okay. Now, persistence and convergence is given by these two lemmas. The value function decreases point-wise in persistence, and for some fixed mutation rate, if we increase the persistence, the value function goes down. And also, the convergence rate to the first best is linear in the discount rate. So that means if we use a token mechanism in this environment, it's not as good as the consecutive number mechanism we are introducing. Okay. Now, finally, we have solved for the optimal mechanism, and we have solved for indirect implementation of this mechanism. The original question we had in mind is the role of transfers. So we want to compare the optimal mechanism with transfer and the optimal mechanism without the transfers. And we have to make a very awkward comparison because we have to compare the optimal welfare maximizing mechanism without the transfer with the optimal profit maximizing mechanism with transfers, because this is the only non-trivial comparison we can make. In both our paper and Bartagnini's paper, if we have transfers, efficiency is trivial. Okay. In our environment, we can charge the agent C for each unit that is provided. So we have to compare to some extent oranges with bananas, but still we want to make this comparison. Okay, now with transfers, efficiency is trivial. And now if we go back to Bartagnini's paper with revenue maximization, we have the observation that inefficiency will decrease over time. And efficiency is achieved along all histories asymptotically. So if you think about the intuition with the ID case, what happens is that the principal will only need to distort the allocation in the first period. And from second period on, we will have efficient allocation. And also the principal only needs to give the agent the information rent in the first period. So the results are very different in these two environments because the logic is different. As I said at the beginning, with transfers, the high type wants to mimic low type. Okay, he wants to hide behind the low type to avoid paying a high price. And with transfers, information rents in period n can be extracted at the very beginning because the future type is very insensitive to my type today. So if we extract future rents at the very beginning, and we can extract more. So this goes to two different functions or two different roles of transfers. Good. And if we have transfers, promises that are made in period n can be cleared in period n. That will help us restore efficiency. And moreover, if we have transfers, we can clear the promises in period in the very future, very far future, at the very beginning. And this allows us to extract information very far in the future. If we don't, and this helps us increase the revenues. And if we don't have transfers, we can do neither. So the only thing we can do is to front load the efficient allocation as long as possible and use the two endpoints to create incentives for the agent. Okay, so that is our final comparison we want to make. Okay. Any questions?
So I think one apples to apples thing you could do is the agent's welfare in the two situations. Does that follow obviously from what you've shown, or is it more difficult to work out?
I mean, if we calculate the agent's expected x-active expected utility. Okay. And I haven't made that comparison, but I think the agent is doing better off in our environment. Okay, because in this case, but it's hard to make the comparison because in that case they have a quasi-linear payoff function, and we cannot talk about the willingness to pay if we cannot pay. So we are comparing, in my mind, two different things. But if you want me to say, I would say in that environment, in the ID case, agent only get one rent, the first period's information rent. But here, the agent gets a promised utility U star. So the size, if we compare these two, I think the size here will be larger in most parameter region. Okay, questions? Okay, now, so all that's missing here, first is a statistical signals, and this has been done by a paper from my colleagues in Northwestern, Lee, Matuszek, and Powell. And so that's already finished. But what we are doing now is to look at more than one agent. So we are not only look at this single agent environment about whether to decide whether to produce or not. We are looking at if we have two different group, theory or empirical, we want to allocate one recruitment slot in every period. How should we allocate based on their reports in every period? This turns out to be much harder, and we started from here and then we move back to single agent, and then we come back again. We still haven't made much progress. And eventually we want to talk about more than one good and more than one agent. So that will be a matching problem in the dynamic environment, like allocating housing, and how should we use this delay time and the future allocations to create incentives. So that is the conclusion picture for my talk. And I end up a few minutes earlier, and it's Saturday, so I think a few minutes earlier is not a huge crime. Any questions? Okay.
Thanks very much.
Thank you.
Thanks everyone for coming to the conference.
Thank you.